So what is indexing? Now we're here. So now we will look at, so what we looked at so far, I always had scenarios like, yeah, there's a relation, we will read all of the relation, yeah, whatever happens. Yeah? But now we will look at more clever ways to access data in a relation, and that's heavily used in query processing. So if you attended the data structures and algorithm class, you will have heard about something like binary search, simple hash tables, I hope. But here we'll look a bit more into the interplay with the storage layer. Yeah, because that makes a difference in the database system. We cannot simply use the data structures from our undergrad lecture here. In particular, we will look at B trees. It's the most important data structure in databases. Was invented 50 years ago now. And there's thousands of different variants of B trees. Hash tables, those two indexes, so index and data structures is a synonym. It's the same thing. Yeah? So the rest of computer science says data structures. Database people say, no, it's an index. Yeah, just to understand. I will always say index, but I mean it's a data structure. Come on. Yeah? So B trees and hash tables are the most important data structures, indexes, of course, in databases. Yeah, we could look at physical data independence a bit, and maybe a little bit at generic and automatic indexing. So there's still research going on in the indexing domain. My group also does something along those lines. We will see. Let's first start with the basics. So what is a B tree, for instance? So here's some motivation. So what is an index? A good analogy from real life is street signs. You go, you go hiking in the Alps and you want to go somewhere. Yeah? You want to find a particular place. Yeah, one idea is, of course, to search the entire Alps for that place. Eventually you find it. Oh yeah, that's what is the place I was looking for. The other approach is to say, no, there are signs. I can follow the signs, right? And every time I follow a sign, maybe I cut the search space in half, kind of. Depends on where the sign actually sits. Yeah? That's basically what a street sign is about. Yes? You don't have to go randomly search through the entire Alps to find a particular place. You follow certain signs. It's so trivial. You do that every day, of course, to save some time. Yeah? Another analogy is, of course, I'm not sure, who of you has seen that, knows what this is? Oh my God, I'm old. Okay. So when I started studying, we also had a library. They had computers, but they also had these drawers with little paper cards. For each book in the library, there was a paper card in a drawer. So if you were searching for something, you couldn't simply go to a search engine, enter some keywords, and then you would get the book, and that's on cupboard, tra-la-la-la-la, and go there. No, there were these large drawers, then organized by topics and author, last name, blah, 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 blah. That's basically what they called an index. How would you find books in the library? So I have to kick that slide. Doesn't work anymore, that analogy. The same as for any street signs. I showed you that. So with that, let's start and give you an intuition for B trees. So as a little sales pitch for B trees before I explain the technique, ping. So it's storage friendly, so it fits super well to the storage hierarchy, not only to the hard disk, SSD, main memory, everything. L2 cache to cache lines, everything. Yeah? It fits perfect in the cache hierarchy. It gives a good trade-off for random and sequential access. You will see how that works. And it's universally applicable. Yeah, so basically what this means is if you understand how B trees work, there will rarely be a need to understand a second index structure in databases. Hash tables, of course. Yeah, hash tables, very important. But if you know B trees, there's no need to reinvent an entire separate index structure anymore. Like almost all indexing problems in the world can be mapped to B trees. Yeah, so it's a matter of taking an existing B tree, tweaking it here, tweaking it there, problem solved. Yeah, that's like for 99% of the problems in databases, that is how it works. So if you understand this, that works in many scenarios. So I give you an intuition, and the idea, so we go back to pages again, and with that you see already why storage hierarchy makes a lot of sense here. So here I'm optimizing the B tree for SSD or hard disk. So I'm saying this is a page, a storage page that I defined. I said, okay, my storage pages are 4 kilobytes in size. And I define here for simplicity that on such a page, I can only store 4 key value entries. It's a bit unrealistic in practice. It's way more, but just for visualization purposes. So 4 key value entries, meaning this is a key, 67, pointing to a value T. Yeah, the value could also be an entire sentence or whatever you want to store on that page. Yeah? So I have 4 entries, 1, 2, 3, 4. But of course, how many key value pairs you can store on a page depends on the size of your key, what is the type, and the size of the value, what is the type of that value. Yeah? Basically, if whatever your page size is 4 kilobytes, maybe let's do the other. If your page size is 4 kilobytes, and your key is, whatever your key is, 4 bytes, and your value is 4 bytes, yeah, then you have 8 bytes, then you divide 4 kilobytes by 8 bytes, and that is the number of keys you can store. How many is that? Is that 512? 512, right? It would be 512 key value pairs you can store in a pair on such a page. Yeah? So far so good? Okay. Okay, now we have this one page. Now I add a second page with data. Page number 2. Now I redistribute the entries. Now you see here, if you look at this one, you see, okay, the stuff is not really sorted. Yeah? 34 is larger than 105, for instance. Now what I do is I sort the data across the 2 pages. Okay. Now we're in a situation where you see, okay, 34 to 72, and then 83 to 105, which means everything here, yeah, everything on the right is strictly bigger as everything on the left, because I redistributed the entries over the different pages. Now what I could add is a pivot element, a descriptor, or what we call it an index page, saying, okay, so here's the 75, meaning if you have anything that's smaller than 75, you go left. If you have anything that's bigger than 75, you go right. Yeah? Like that, you could find data. You could search this structure to find the appropriate data item. Yeah? Let's add another page with more data. Yeah? So now, okay, these data items are all over the place. That belongs here. 15 is also here. 73 would be here. 102 would be here. Yeah? All over the place. So with the algorithm I'm explaining you, this very stupid algorithm, you would have to redistribute all of the pages, the data over the pages again. Don't do that in practice, but that's how it will look like. Now you have 3 of those pages, the blue ones, and you have to fix the descriptor. Yeah? So here we only have 1 entry for the moment, so let's fix that as follows. Now I'm saying, okay, here's a 60 and there's an 84. If it's 60, you go here. If it's 84 or bigger, you go right. And if it's 60, including or smaller 84, so in between those 2 values, in other words, you go here. Yeah, so the descriptor allows you to find the appropriate data item. I know what you will ask.
Maybe not, but you're sorting on the keys.
Yes.
I mean, if I look into a database, I don't know the key in advance, do I? I just know I want to have the record of Peter's salary.
Yeah.
So, where's the connection to the actual data?
Okay, so the connection to the actual databases, so whatever you define as your primary key, it's typically used underneath by the database system. It will create an index on that already. But you can still create additional indexes. Now, if you say you're interested in attribute foo, to have index access on that, you can there's a command for that, create index on tra-la-la-la-la-la-la, and the database will create an index for you, and then those values here correspond to your attribute values foo, and the entries here point to are pointers to rows in the relation. Yeah, like that you can create actually almost as many indexes as you wish. Yeah? That was unfortunately not the question I was expecting. Anyone else has a question I'm expecting? No. Okay, so I must have to do a rhetorical question. Yeah.
So what happens when we add a new row?
Yeah. What happens if we add a new row? Yeah, because we can't redistribute always over it's stupid, right? What I just showed you is stupid. Just gives you an idea how the stuff is organized. No, I'm more interested in this actually. So 84, I said 84 including and everything strictly greater than 84 goes to the right side, yeah? Which means this is read as 60 including, 84 not including, so it's a half open interval. Yeah, it's something like 60, 84, yeah, that's this stuff. The third leaf is 84, something like that, and this is 60 excluding, 60 excluding minus infinity. Minus infinity. Yeah, that's basically this guy here. Yeah. Why did I put the 84 on the left side of the interval, not on the right? Why would it have an advantage to put it on the left side of the interval rather than on the right? Yeah?
Because it's in the middle, and then that space there would be limited.
What would be?
Limited. So
You mean for this leaf in the middle from 67 to 83, this is the interval, maybe I write it again with the other pencil tool. Yeah. So basically we said this descriptor has this interval 60, 84 excluding. Yeah, that's this guy. Yeah. And then on the right it's 84 including plus infinity. But I could swap the roles. I could say, okay, now in my world, I would put 84 here. Yeah, the rule I'm making here in searching the data is I mean, the interesting question is when you're looking for 84, you have to know, do I go left or do I go right? Is 84 included on the right side or on the left side? Yeah. Right, you just have to make it consistent. The answer is it doesn't matter. Yeah, it has to be unique throughout the whole tree. Other than that, it makes no difference whatsoever. Yeah, and here I made a decision, okay, 84, so if it's the same value, always go to the right. Other than that, it doesn't make any difference. So you will see examples where equality sometimes goes to left, to right. Yeah, just if you have doubts, think about, okay, how is it meant? How did they use equality here? And then it's clear. You know? It's a little, it's a thing that comes often in these discussions. Okay, so now we can use this algorithm and recurse. And don't worry, I will show you a better algorithm. This is not an algorithm that would be used in practice. So B-tree has two major other approaches to actually insert data. We will look at that. But for the moment, let's look at some properties of a B-tree. So we have two types of pages here. We have those green pages, we call them nodes. Sometimes they're called inner nodes. Those are nodes. This in addition is called the root node, and the blue guys are called leaves, okay? And now we can look at the properties. We look first here. So there are two parameters, one is k and the other is k star. So here the constraint in the nodes is node has k to 2k stars. So the minimal number of, again, a node has k, the minimum is k keys up to 2k keys. Yeah? Keys using, serving as pivot elements in this case. And if you think about that, for one key in a node, you have two arrows. Yeah? You can differentiate two different subtrees, two different arrows can be separated by one key. Whenever you add a key in a node, you can also add another arrow. This means the number of keys plus 1 is the number of arrows, the number of pointers to children nodes in such a structure. Yeah? N plus 1, whereas in the leaves, you don't have pointers because that's the last level of the tree. And here it's k star to 2k star entries, that's this one, which means for both structures, this means those nodes are half full, are at least half full. Yeah? At least half full to fully occupied. The same holds for leaves, half full to fully occupied. That's the rule. It's in textbook B trees, in practice other rules, but there's a textbook truth. There's a special case, and that is the case when one of those, either a node or leaf, is the root. Yeah? There can be only one, of course. Then these constraints are dropped. Yeah? Then there can be from 1, now we're here, yeah? From 1 to 2k keys, and here it can be 1 to 2k star key value pairs. Yeah? There the rules have to be dropped. Why? Yeah, if you think about this one, why would you do a 1 here in this case? Yeah? I didn't get the first part again.
The page doesn't have to be full. For the page to exist, it just needs one even pair.
Yeah, we had it kind of right. We had it kind of here in this situation. Assume that this is your data. That's all the tuples you have. So all your data fits into a leaf. This leaf is also the root. This is the root node of your B tree. There's no internal node. There's just one leaf. Yeah? And the extreme case is your data consists of a single tuple. Yeah? Then this leaf would underflow. Yeah? This would all be gone. Yeah? Only one tuple. You still want to be able to create a B tree for a single tuple. Yeah? Therefore, you have to soften this constraint. Okay, very good. Time was 10 minutes left. Okay. So those are the properties. And the tree itself has interesting properties. So one is, we will see why how that is maintained. The path from the root to any leaf has always the same length. It's a perfectly balanced tree. And you might have heard about balanced trees in the context of binary search trees, red-black trees, AVL trees, and stuff like that. Difference maybe 1, 2, whatever. You define it. I think typically the difference is 1 in length or something like that. Here the length of a path from the root to any leaf is always exactly the same across the entire tree. We will see how that works. Yes, explained, k and k star are implicitly defined, depends on how, which data types you use for your key and your value, and also the pointer size. You use pointers in the inner nodes, so how much space do you require for a pointer. There are no values in the index nodes. That's very important. So you saw it here. Yeah, there are no value entries here. These letters, those are my values. They don't exist in these inner nodes, in the green nodes. That's a very important property. We will exploit that later on. All data sits in leaf nodes. Data inside nodes and leaves is sorted by key. Yeah, and that allows you to do a binary search within a leaf. But I'll explain those properties in a moment. This is again what I already scribbled 5 minutes ago. So you can read a B tree as a recursive interval partitioning. Yeah, so when you start from the root node here, so what this descriptor is saying, and here again I'm assuming that equality means it goes to the right as before. So this guy here, this root node partitions the data or partitions the tree into subtrees. And each subtree, for each subtree, there's an invariant you can identify. And the invariant is here that the subtree on the left can only represent data from -infinity to 60. Subtree on the right, 123, including to +infinity. There's a bracket missing here, whatever. And in the middle, it's 60, including to 123. And so forth recursively. Yeah, so if you go to the next level, it's the same game again. Here you make that interval more narrow, and then you would say 63 including to 103 excluding, and so forth. It's a recursive interval partitioning. Okay, find key. The key should be clear. So basically, you start with the root, and then you recursively search the structure. So if you want to find the key 67, for instance, you have to choose the subtree. You have to find the right subtree to proceed your recursion with. Yeah? So here, 67 is clearly in this interval. So you go down this arrow and you search within the leaf. You reach the leaf, and that means within the leaf, you can do a standard binary search algorithm. Why not? If the data is sorted in the leaf, you can do binary search. If the data is not sorted, you would have to do linear search through all entries. But binary search here is typically the better idea. If you want to find a range of values from 34 to 72 including, okay, then you basically have to flop the tree. So you have, what I'm saying is you may have to go multiple pointers at the same time. Yeah? Basically, you can look at the left boundary of the interval, 34, and the right boundary, 72. So you go down the 34 arrow, this one. Within the leaf, you find, okay, that's the first entry. Then you go down the 72 arrow, that's basically this one, find it, and then everything in between would be your result. Yeah, there could also be entire subtrees in between, makes things more complicated. And this is not very helpful in a B tree, in a database, and that is why other techniques were invented. And this is called an index sequential access method, which converts the tree into a graph. So what we add is, we add pointers on the leaf level. So this leaf gets a pointer to that guy. You see it here. Yeah? So it's a pointer there, and backwards. So you get forward and backward pointers, which allows you to make a range query more efficient. Now, if I do a range query, what I do is I basically only search for 34, make a standard point query, I run down the appropriate path, I end up with this guy, and then I scan across the leaf layer. I basically scan, I keep chasing those pointers, I keep evaluating those keys as long as the key I'm looking at is smaller equals 72. Yeah? Once I find a key like here 73, which is strictly bigger than 72, I stop. Yeah? Like that, an interval is typically more efficient. That's called index sequential access method. Okay, now let's look at the B-tree main operations. And the question was, how do I insert? Obviously not how I explained it at the beginning of the slides. That wouldn't make sense. Actually, I think the complexity of what I showed you in the beginning is like squarish. To think about that, I think so. Every time you resort, if you do it per tuple, that's even worse, right? N times n log n can be pretty bad. Anyway, so let's assume we want to insert something. So how does it work? So basically, the first thing you do is you do a query. You want to insert a key value entry where the key is 74. The first thing is your query. So basically, you find the appropriate place where that would have to be inserted. Yeah, 74, you follow this arrow here, you end up in this leaf. This leaf is already fully occupied. So you don't have room for a new tuple there. So you have to do something about that. This redistribution thing, probably not. There's a better algorithm. And what we do is, in this situation, is called a leaf split. So what you see here is I created a new leaf. I even created a new entry here in that node. Yeah, now I have 4 leaves with 4 pointers from the descriptor rather than 3 as before. Yeah? So what I did was I took the existing leaf, I split it into 2. I said, okay, 67 and 72 is on one leaf. I create a new leaf where I put 73 and 83. Yeah, that's my new leaf. And then I fill the page in the right place. You see it on the next slide. Yeah, here's a, so this is the old page. I removed those 2 entries. I put them here on the new page. Yeah. And then I do the insert. Now I have room again for 2 more elements. 74 belongs in between 73 and 83. So I fix the errors here, the ISM order, and I have to do another entry here such that the invariants are maintained. That is the operation that happens here. That's called a B-tree split operation. And we will look in more details on how that works. So here's a summary again. That is the before situation. That's the after situation. The question is, how do you do that algorithmically? So high-level message of course, is for the moment, when there's an insert and there's no room in a leaf, the B tree will handle that automatically and will keep maintain all the variants. I think we start with that. I think we should repeat that anyway next time. So here's pseudocode for how that insert operation works. And I do it in an object-oriented fashion. So I assume that there's an abstract node. So a node, a super type that cannot be instantiated. And I have my different node types. So that's the inner node, or node for short, and I have the leaf. And I'm presenting here the 2 insert algorithms in kind of Python notation. It's not only kind of, I think it is Python notation. We have a Python implementation where we took that algorithm from. And I have an insert operation for the leaf, and I have an insert operation for the node. And I think I start explaining that, and next time we start all over from that again anyway, because it's super important. So basically, I call this method with the key value pair I want to insert. So what I do is, I first, as I'm in an internal node that has pointers, I have to make a decision which arrow am I going to chase, which arrow am I going to follow down the tree, and that is done by this operation called choose subtree. That's basically this query I'm doing on the tree. So now I know, okay, that is a subtree where this key belongs. Now I call insert on the subtree. And as I'm in an object-oriented modeling world, I don't know the type of the subtree at this point in time. So depending on the subtree, it may be an internal node, again, with pointers, or it may be a leaf. So depending on the type of the node, object orientation, polymorphism, I will call again this method if it's a node, or if it's a leaf, of course, I will run into this method, which is the leaf. Yeah? So if you go back at the situation we just had, well, we enter a leaf that is full. So what the leaf actually does, I mean, eventually I get the insert operation in the leaf. And what the leaf does, it performs the check, okay, do I have room? So if the number of keys is already at the limit, then I have to do something. If there's room, that's this else, then I simply insert it on this leaf. Everything is fine. That's the easy case. The more complex case is what happens if there's no room available. And that happens here. And that's called a B-tree split, which is propagated up the tree recursively. And how that works, we will look at next week. Thanks.